Hello guys, my name is IBM. A lot of you are always asking where am I based. I'm based in Mongolia, in Ulaanbaatar, the coldest capital of the world. Today I want to solve another paper, which is 9702, paper 42. This is advanced level structured or A-level structured questions for the May-June series. Like I said, I will not solve for 3 because 4.3 and 4.1 are the same, and I've already solved for 1. So let's see the question paper. So here is the question paper that we are here to solve. It's what's wrong with this? Okay, so it's May-June 2024. It's supposed to be 2 hours. I may use more time. I will not go through the instructions. I will not go through the data. I will not go through the formula. You can go through all those ones. I'll go straight to the first question. Define a radian. So remember, for angles measured in radians, the angle delta theta is equal to S over R, where S is the arc length and R is the radius of the circular path. So when we have delta theta as 1 radian, that is when S equals to R, so that they cancel out to give us 1. So we shall define a radian as the angle subtended at the center of the circle, or the center of a circle, that is when the arc length equals to the radius of the circular path. So that's what we call the radian. A circular metal disc spins horizontal about a vertical axis, as shown. A piece of modeling clay is attached to the disc. For the instant when the piece of modeling clay is in the position shown, draw on the figure an arrow labeled V, showing the direction of the velocity of the modeling clay. So we see that the rotation is anti-clockwise. So at every point, the velocity is always tangential. So is a tangent to the direction of the path. So it is going to be in this direction here. Because it's moving anti-clockwise, if I was to trace a circular path around here, then the tangent to the circular path is going to be the direction of the velocity. So I'll just draw a tangent somewhere there. So I'm going to draw an arrow somewhere here. And they said label this V. So the arrow will be somewhere there in that direction, because there's always a tangent at every point. Because it's moving anti-clockwise, it is going to be somewhere there. Then an arrow labeled A, showing the direction of the acceleration of the modeling clay. Of course, the acceleration acts towards the center because the force is centripetal force. So I must draw a line which points towards the center. These two must be making 90 degrees, of course. Okay, so that is pointing towards the center, and I said we should label this line A. Then the metal disc in the figure 1.1 has a radius of 9.3 centimeters. The center of gravity of the modeling clay is 1.2 centimeters from the rim. That means the distance from the center to where the modeling clay is going to be 9.3 minus 1.2. The distance from the center to the modeling clay is 9.3 minus 1 point, which is going to be the radius of its circular path on the disk. Then calculate the angular velocity. So we already know that v, angular speed, a linear speed is equal to the angular speed times the radius of the circular orbit. So the angular speed is going to be the speed v divided by r, which is going to be, they gave us the speed as 0.68 divided by the radius, which is going to be 9.3 minus 1.2 times 10 to the power of minus 2. I know many students must have failed to remember to subtract 1.2. So this is 0.68 divided by 9.3 minus 1.2 exponent minus 2. Oh, the calculator doesn't allow that. 9.3 minus 1.2, the answer is that times 1 exponent minus 2. Then I will divide 0.68 by the answer. So this is giving me 8.4. So the angular speed is going to be 8.4 radians per second. Calculate the acceleration A of the center of gravity of the modeling clay. Of course, the force acting here, we know this is the centripetal force, which is the mass times the centripetal acceleration. But of course, we know that centripetal force is mv squared divided by r. So when I compare the equations, it means the centripetal acceleration is going to be simply v squared over r. So I'll substitute here. It will be 0.68 squared divided by r, which is 9.3 minus 1.2 times 10 to the power of minus 2. Alternatively, you could also look at this as centripetal acceleration being equal to omega squared times r. If you try to manipulate these equations, if v is equal to omega r, if v is omega r, this would be the same as omega squared times r, which would be omega, remember, is 8.4 squared, then times r, which will be 9.3 minus 1.2 times 10 to the power of minus 2. I think it gives us the same answer. So I have 9.3 minus 1.2. The answer times 1 exponent negative 2. Then I'll say 0.68 squared divided by the answer. So that is 5.7. So the acceleration here is going to be 5.7. I think it's the same answer here, 5.7. You can check this method too. Then the second piece of modeling clay is attach the disk in the position shown. Okay, so we notice that it's brought closer to the center. So it's like the radius has reduced. Second piece of modeling clay has a larger mass than the first piece. So it has a larger mass than the first piece. By placing one tick in each row, complete the table to show how the quantities indicate or how the quantities indicated compared for the two pieces of modeling clay. So let's begin with angular speed. Of course, we know that the angular speed is equal to v over r, but in practice, the angular speed is the rate of change of the angular displacement, that is delta theta by delta t. So in practice, the angular speed is going to be the same, because even though r is different, it is not going to entirely depend on the radius of the orbit, because they're orbiting the same center. It is going to be just the rate of change of the angular displacement. So this is going to be the same for both. The angular speed is going to be a constant, which is going to be the same for both. But Because the radius is different, then V is equal to omega times R. Even though this is the same for both, the radius is not the same. That means V is not going to be the same. But note that the radius for the second one is smaller. So it means V is going to be less. The linear speed is going to be less for the second piece. So I'll put a tick here because the radius for the second one is less than the radius for the first one. So V for the second one is going to be less than V for the first one. Then acceleration. So if the acceleration is also equal to omega squared times R, remember omega is the same for both because it's a constant. The angular speed is constant. So this means it is R which is changing and R2 is less than R1. So it means also A2 is going to be less than A1. So I'll put a second tick here. As simple as that. With reference to thermal energy, state what is meant by objects being in thermal equilibrium. Remember from what your teacher mentioned in class, when two objects are in thermal equilibrium, the temperature is the same, so the temperature difference is zero. And if temperature difference between two regions is zero, it means there will be no net flow of energy from one point to another. So I'll simply say the two objects are at the same temperature two objects are at the same temperature, and so there is no net transfer. You must mention net. There is no net transfer of thermal energy between them. So energy flows uniformly between the two objects so that there is no net transfer in any particular direction. That's why we say they are in thermal equilibrium. Two cylinders X and Y each contain a sample of an ideal gas. The samples are in thermal equilibrium with each other. X has a volume 0.026 meters cubed. It contains 0.70 moles of gas at a pressure of 1.2 times 10 to the power 5 pascals. Y has a volume of 0.0430 meters cubed. It contains a pressure of 2.9 times 10 to the power 5 pascals. Data for the two cylinders are shown. Show that the temperature of the gas in X is 234 degrees Celsius. Remember, these are in thermal equilibrium. That means the temperature for X is the same as the temperature for Y. As simple as that. Show that the temperature of the gas in X is 234 degrees Celsius. So we know that PV is equal to nRT. So the temperature is going to be the pressure times the volume divided by N times R. I'll just substitute. The pressure is given as 1.20 times 10 to the power 5 pascals, and the volume is given as 0.0260. Then the number of moles is given as 0.740. Then times the molar gas constant is known as 8.31. So I'll just press my calculator. 1.2 exponent 5 times 0.026 divided by 0.74 times 8.31. So this is giving me 507. I'll write three significant figures because they try to give us not less than, everywhere it is three significant figures. So I'll write three significant figures here to maintain the same degree of accuracy. So 507 Kelvin. So, but to change the temperature to degrees Celsius, this is going to be 507 minus 273. And when you subtract, I think this gives you 234 degrees Celsius as required. Then determine the number n of moles of molecules of the gas in Y. Number of molecules. So remember PV is equal to nRT, but also PV is equal to nKT. The examiner said explain your reasoning. So, and we want the number of molecules. So since the sample is in equilibrium, the temperature is going to be the same. So I'll say since the samples are in thermoequilibrium, since the samples are in thermoequilibrium, then the temperature of X and Y is the same. So I'll just now you make n the subject. N is going to be equal to PV divided by K times T. So P for Y, I think it is 2.90 times 10 to the power of 5. Then V for Y is 0.043. So this is 0.0430. Then I'll divide this by Boltzmann's constant, which is given 1.38 times 10 to the power of minus 23. The temperature is going to be the same, but I'll use Kelvin. So this is 507. You can't use 234 degrees Celsius because every time we use these equations, the temperature must be in Kelvin units. So I have 2.9 exponent 5 times 0.043 divided by 507 times 1.38 exponent minus 23. So I'm getting 1.78. To three significant figures, 1.78 times 10 to the power of times 10 to the power of 24. Okay, I think that is all. The gas in X consists of molecules that each have a mass that is 4 times the mass of a molecule of gas Y. So we are seeing that the mass of X, molecules in X, is 4 times the mass of molecules in Y. Okay. Explain how the root mean square speed of the molecules in X compares with the root mean square speed of the molecules in Y. Of course, we know that kinetic energy EK is a half m. So this is the mean translational kinetic energy of a molecule, which is a half m times the mean square speed, which is the same as 3/2 times kT. So this means if I make C the subject, it means the mean square speed is going to be equal to 3 kT divided by m. The 2 has cancelled. So when I find a square root, I find the root mean square speed is going to be the square root of 3k. So C root mean square is 3 kT divided by m. Okay. So 3k and t are constant because they said because they were the same temperature. So I'll simply say C root mean square speed is equal to a constant divided by root of m, because root of 3kt is a constant. Okay, so let's say I'll say C for y is equal to k over root of m. Therefore, C for x, because they say the molecules of x have a mass which is 4 times. So C for x is going to be k divided by 4 times m. So it will be root of 4. What did I write here? Okay, so it is root of 4m. If x is m, the other one is 4 times m. So when you compare the two equations, I'll just compare x and y. Let me just compare x and y. So I'll say Cx divided by Cy is going to be equal to K over root of 4m times reciprocal root of m over K. So this is K is cancelling. So this is 1 over, I think this is 1 over 2 because root of m also cancels and you get the root of 4. Root of 4m is 2 root m. So root of m cancels, you get half. So it means it's like Cx is a half of Cy. Okay. This is just to show you, but I can write this without even, I can answer this without even writing that working. So I'll simply say from Ek equals to 3 over 2 times Kt, then the mean kinetic energy of molecules is directly proportional. Is directly proportional to the absolute is directly proportional to the absolute temperature. Since temperature is the same, the mean kinetic energy is the same. Since temperature is the same, then the mean kinetic energy is the same. Does it mean the root mean square speed is also the same? Not at all. Then also I'll say from Ek equals to half m mean square speed. It means kinetic energy is proportional to the mass. So kinetic energy is proportional to mass times speed squared. Let me say times the mean speed squared. And so the root mean square speed is inversely. When you combine those two, you see it is inversely proportional to. The root mean square speed is inversely proportional to the square root of the mass. I think we have seen it here. It is inversely proportional to the square root of the mass. So the root mean square speed is inversely proportional to um, the root of the mass. So what conclusion can I give? Hence, the root mean square speed of molecules in X is half the root mean square speed of molecules in Y. And by the way, I can just draw this fill that gap with this calculation and write a conclusion. This can be my conclusion. I can just fill that gap with a calculation. So it is because this calculation is entirely implying the same thing. This one has been mentioned. We have combined the two, and we have arrived at this, so it's the same thing. Okay, state what is meant by internal energy of a system. Of course, we know what internal energy is. Internal energy is the sum of the kinetic energy plus the potential energy of all the molecules that make up the system. But remember, the molecules are always in a continuous random motion. So we shall say internal energy is the sum of the random distribution. The sum of the random distribution of the kinetic energy and potential energy of all the particles. You can call them molecules, or the particles that make up the system. The sum of the random distribution of the kinetic energy and the potential energy of all the particles that make up the system. With reference to molecular kinetic and potential energies, describe and explain how the internal energy of the system changes when a gas is heated at constant volume so that the temperature increases. Here the temperature increases, it means the kinetic energy part is increasing. The volume is constant, it means the separation is not changing. That means the potential energy component is there is no change in volume, so there is the molecular potential energy is not going to change. But remember, internal energy is equal to the kinetic energy plus the potential energy. Even though the potential energy is not changing, the kinetic energy is increasing, so the internal energy is going to increase. So for that one, I will simply say at constant volume, no change in separation. There's no change in separation of the molecules. What does that mean? So no change in molecular potential energy. So there's no change in molecular potential energy. However, increase in temperature means the kinetic energy of the molecules increases. So increase in temperature. Increase in temperature means kinetic energy of molecules increases. So if one of them has increased, then I'll simply say that increase in molecular kinetic energy means the internal energy increases. So increase in molecular, that is kinetic energy of the molecules, increase in the molecular kinetic energy, increase in molecular kinetic energy means that internal energy increases. So it means because the molecular kinetic energy has increased from internal energy equals to kinetic plus potential, so it means the kinetic internal energy increases. Then a wire is stretched. That means if the decrease in cross-section area is negligible and there's an increase in length, it means the volume increases. So the volume is increasing within its elastic limit at a constant temperature. So here it means the kinetic energy remains constant, so the change in kinetic energy will be zero. So it still means our internal energy increases. So I'll start with the constant temperature part, and I will say constant temperature. Constant temperature means no change in the molecular kinetic energy. No change in the molecular kinetic energy. But we are seeing stretching, so the separation increases. So separation increases, or separation of molecules increases. So potential energy of molecules increases, and I will simply say the increase in molecular potential energy means an increase in internal energy. Increase in the molecular potential energy means internal energy increases, means that internal energy increases. Okay, so I think that was maybe it was the question where my students might have lost a few marks, I think, because they can't write all these important points. They may miss out one or two. Simple harmonic motion: a block of mass m oscillates vertically on a spring as shown in the figure. The acceleration a of the block varies with displacement x from its equilibrium position as shown. Okay. The amplitude of the oscillations is 3y, and the maximum acceleration, so this is going to be a naught. This is going to be x naught. Explain how the figure shows that the oscillations of the block are simple harmonic. So we see that is a straight line to the origin, which means acceleration is directly proportional to displacement. Number two, we see that the gradient of this line is negative, which means the acceleration and displacement are always in the opposite directions. So I'll just write that straight line through the origin shows that acceleration is proportional to displacement. Number two, the negative gradient of the line shows that let me write in full, acceleration and displacement are always in opposite directions. Okay, so that is how we can conclude that the motion is simple harmonic. Did you say expressions in terms of sum or all m, a, and y for the angular frequency omega? So we know that from the general definition of acceleration, simple harmonic motion, a is equal to negative omega squared x, which means if I compare with y equals to mx plus c, it means that the gradient is going to be negative omega squared. But note that the gradient itself is negative. So I will say negative omega squared is equal to, so let me find a gradient. I'll just take one part of this graph. Let me take this part here. So here we have 2a, and here we have negative 3y minus 0. So the gradient is going to be 2a minus 0 divided by negative 3y minus 0, which is equal to negative 2a over 3y. So the negative cancels out. So we shall have that omega squared is equal to 2a divided by 3y. Then I find the square root. Omega squared will be the square root of 2a divided by 3y. So the answer here is going to be the square root of 2a divided by 3y. Then the maximum speed v naught. Of course, we also know from our knowledge from class, we know that v naught is omega times x naught. So this is going to be the square root of 2a over 3y times the maximum amplitude, which is 3y. So to bring this into the brackets, I'm going to square it. So this is going to be the root of 2a over 3y times 3y squared, and bring it into the root. So one of the squares cancel with that, so you remain with the root of 2a times 3y, which gives us the root of 6ay. So the answer here is going to be the square root of 6ay. I think I write square root badly. Then the energy, of course, we also know from our knowledge that energy is going to be equal to a half m omega squared times x naught squared. So I'll just substitute. So this is a half times m. Where there is omega squared, I'll just put 2a over 3y. So this is times 2a over 3y. Where there is x naught squared, remember x was 3y, so I'll just simply say 3y, but the whole of this is going to be squared. So the square here cancels with this. This 2 cancels with that. So I remain with 3y ma. So this is going to be 3y a times m. The order doesn't matter. Then the period of the oscillations is 0.75 seconds, and the value of 3y is 1.8 centimeters. So remember this was the amplitude. Determine an expression for x in terms of time t, where x is in centimeters and t is in seconds. So they did tell us when timing starts. So the expression can either be x equals to x naught sine omega t, or it can be x equals to x naught cos omega t. So all I need is to find x naught, to find omega. So omega, angular frequency, is 2 pi divided by t, or I can just substitute in the equation, but I don't know 2s, so I will not use that. I will just use 2 pi divided by t. So this will be 2 pi divided by the period t, which has been given as 0.75. So 0.75, what is this? I think that is 8 over 3 pi. So this is 2 pi divided by 0.75. So this is 8 over 3 pi, or 8.4. Of course, this is radians per second. So I'll write my equation as either x equals to x naught, which is 1.8 sine of 8 over 3 pi times t. So let me write here x equals to 1.8. You can change that to meters. 1.8 sine of 8 over 3 pi, then times t. Or you can write 1.8 cos divided by, let me use 8.4 times t. I'm using both because they did not tell us when timing started. If they had told us the timing started when it was at maximum displacement, then we would know. But none of them shows the value of x when t equals to 0. So either of these would be correct. Any of these would be correct. So define electric potential at a point. I think we defined gravitational potential. Now we define electric potential in this paper. Gravitational potential was in 4.1. Now let's define electric potential. For gravitational potential, we consider the mass. For electric potential, we are going to consider a unit positive charge. So this is simply going to be the work done per unit charge in moving a positive charge from infinity to the point. So that is electric potential. Two isolated charged metal spheres X and Y are near to each other in a vacuum. The centers of the spheres are 1.2 meters apart as shown. Okay. Point P is on the line joining the centers of the spheres X and Y and is at a variable distance x from the center of X. The figure 5.2 shows the variation with x of the two electric potential V of total electric potential. So this is total electric potential V due to the two spheres. So when we say potential is constant, means we are inside one of the spheres. For example, it is constant up to here, so we are inside one of the spheres, then it now goes to minimum, and again it becomes constant, which means we are now inside another sphere. So this distance here is going to be the radius of this sphere, maybe x, and this distance is going to be the radius of the other sphere, maybe y. State three conclusions that may be drawn about the spheres from the figure. The conclusions may be qualitative or quantitative. I think such a question appeared almost the same question, maybe in Feb, March, I don't know. So number one, let's start with the radii. So the radius of sphere X is, I think that is 0.3. This is 0.3, and this is 1.2 minus 1.5, which gives us 1.2 minus 1. No, this is 1.1. So this is 0.1. Okay. So this distance here is 0.1. So the radius of sphere X is 0.30 meters. Is it in meters? Yes. And the radius of sphere Y is 0.10 meters. Or I would simply say radius of X is equal to 3 times radius of Y. So I could simply say this: radius of X is 3 times radius of Y. Okay, then let's look at the charge. I think both charges are positive. The charge of X is positive, the charge of Y is positive because the potential is always positive. So I'll simply say charge of X is positive, charge of Y is also positive. Or I would simply say the spheres X and Y carry charges of the same sign. So the spheres are carrying charges of the same sign. Both of them are positive. Why? Because potential is equal to kq over r. Potential is positive when the charge is positive. It is negative when the charge is negative. But since potential is not changing direction, it means it's positive throughout, which means both charges are positive. Okay, then the other one I can talk about the magnitudes. Let me check the magnitudes of the charges. I think the magnitude is the same because let's see if the potential is minimum at the center between the two charges. If the potential is minimum at the midpoint, remember the midpoint, the distance r is the same. So if the total potential is minimum at the midpoint, it is only because the charge between the two spheres is the same. So let's check. So where is potential minimum? We notice that potential is minimum here, which is at a distance of 0.6 meters from each of the centers. Because potential is minimum at the center between the two charges, it means the distance from each of the centers, remember potential is equal to kq over r. And we are seeing that, of course, effective potential V would be equal to, V resultant would be kq for X over R for X plus kq for Y over R for Y. And because the potential is minimum at the center, it's only because, remember, R is the same for both. R is the same for both. So if R is the same, let me just call it R. So it means effective potential will be R times V resultant is going to be KQX plus KQ of Y. R is the same, K is the same, so I'll just cross out those quantities which are the same for both. So it's like the resultant potential is directly proportional to the sum of these charges. Therefore, I would simply say because the potential is minimum at the center, minimum potential is at the midpoint, then it is only because the charge on each of the spheres is the same. If the charge on the X was greater, the minimum potential will be closer to the right-hand side. If the charge on Y was greater, then the minimum potential will be closer to the left-hand side. But since the minimum potential is just at the center between the two spheres, then the charge on each of the spheres is the same. So I'll simply say the magnitudes the magnitudes the magnitudes of charges on the spheres are equal. The reason is because potential is minimum, since potential is minimum at the midpoint. Between the two spheres. So potential is supposed to be minimum closer to a sphere which has a smaller charge. But since the potential is minimum at the midpoint, it's only because they carry the same magnitude of charge. So those would give you the 3 marks, I think. A proton is held at rest on the line joining the centers of the spheres in B at the position where x is 0.6 meters. That's at the midpoint. Describe and explain without calculation the subsequent motion of the proton. They said without calculation. So potential is minimum at the midpoint. Of course, these are like charges. It means where the potential is minimum, or where the total potential is minimum, the resultant electric field strength is going to be 0. And remember, E is equal to F over Q. Because E is 0, F is going to be 0, and F is equal to ma over Q. So it means the acceleration is also going to be 0. What does that mean? When a proton is placed at that point where potential is minimum, it will not move at all because the resultant force on it is 0. So it means the acceleration will be 0, so it will not move. So I'll simply say at x equals to 0.60 meters, potential energy of the proton is already minimum. It can't go below that. It's already minimum. Is already at its minimum. Is already at its minimum. Is already at its minimum since the forces from the two spheres on the proton are equal and opposite. So at when the potential energy of the proton is already minimum at its minimum, since the forces from the two spheres on the proton are equal and opposite. So the potential energy at that point is already minimum because the forces are equal but opposite. That means the resultant electric field is equal to zero. Normally, the potential energy is minimum when the forces are equal but opposite. So because there is no resultant force, I'm just adding on this because I'll put this one below because there is so I'll say because there is no resultant force on the proton, it remains at rest in the position of release. So at x equals 0.6, it's already at its minimum potential energy. It's the potential energy of the proton is already at its minimum. So if we release it at that point where there is no resultant force, it will just remain at rest. Okay. Then two capacitors X and Y are connected in series. Remember how we find total capacitance in series as shown in the figure. The capacitance of X is Cx and the capacitance of Y is Cy. Derive an expression in terms of Cx and Cy for the combined capacitance. Explain your working. That's what people normally forget. So we know because the capacitors are in series, then the charge on both capacitors is the same. So charge on both capacitors is the same, and I will call it Q. And of course, it's the same as the effective charge. So using potential dividers, effective PdV is going to be the PD across X plus the PD across Y. Of course, the V is divided here. This will be Vx, and this is going to be Vy. So also remember that capacitance C is equal to Q over V, or Q is equal to C times V, which means V is going to be Q over C. So V will be Q over C. So this will be Q over C equals to Q over Cx plus Q over Cy. So I have that Q over C is equal to Q into 1 over Cx plus 1 over Cy, and this Q cancels out. Hence, 1 over C, that is effective capacitance, is going to be 1 over Cx plus 1 over Cy. So that's how we find capacitance in series. So two capacitors P and Q are connected in parallel to the power supply voltage V. The capacitance of P is 2000 microfarads. The capacitance CQ of Q can be varied between 0 and 400 microfarads. When CQ is 0, the total energy stored in the capacitor is 2.5 millijoules. CQ is 0. So it means total capacitance is just 200 microfarads. So show that the supply voltage is 5 volts. So energy is equal to a half times C times V squared. So I want to find V. So V is going to be twice E divided by C under the square root. So I'll just substitute square root of 2 times 2.5 times 10 to the power of minus 3 divided by the capacitance, which is 200 times 10 to the power of minus 6. I'll check my calculator. 2 times 2.5 exponent minus 3 divided by 200 exponent minus 6. Then, of course, the square root is 5. So this is going to be 5.0 volts. Then the next question is calculate the total energy in millijoules stored in the capacitors when CQ has its maximum value. So let's first find total capacitance. So total capacitance, because they are they said they are joined in parallel. Initially they were in series. Here they are saying they are connected in parallel. So since that they are now in parallel, so this is going to be 400 plus 200, which is equal to 600 microfarads. For capacitors in parallel, we sum up to get total capacitance. So it means the energy stored now is going to be a half CV squared, which is going to be, of course, V will not change. So this is going to be a half times 600 times 10 to the power of minus 6, then times 5.0 squared. So I'll just press my calculator. Half is 0.5 times 5 squared times 600 exponent minus 6. So this is 7.5 times 10 to the power of minus 3. 7.5 times 10 to the power of minus 3 joules. But here they want the answer in millis. So this one, 10 power minus 3 is in millis. So I'll just write here 7.5. On the figure 6.2, sketch the variation of the total energy stored in the capacitor with CQ as CQ varies from 0 to 400 microfarads. Okay, I'll use a simple expression here. Capacity, total energy stored is a half CV squared. When CQ equals to 0, the energy stored is just due to the first capacitor, and it was 2.5 millijoules. So we shall plot a point which is 0 and 2.5. That's 1. Then when CQ equals to 400 microfarads, the energy stored we have already seen to be 7.5 millijoules. So the second point I'll plot will be 400 and 7.5. And we also notice that energy is equal to a half Q. I think energy is going to be a half QV. So it means energy is directly proportional to V, and energy is directly proportional to capacitance. That is a straight line without wasting time. So 0 is 2.5, then 400 is 7.5. That is a straight line. Okay. Then this is magnetism and electromagnetic induction. State what is meant by state Faraday's law of electromagnetic induction. Remember, Faraday's law is magnitude, Lenz's law is induced is direction. So I'll simply say the magnitude of induced EMF is directly proportional is directly proportional to the rate of change of the magnetic flux linkage. That is Faraday's law. The figure shows a coil at rest in a uniform magnetic field that is parallel to the axis of the coil. It's parallel to the axis of the coil. Okay. The coil is connected to a center zero voltmeter. The flux density B of the uniform magnetic field varies with the T as shown. The coil consists of 400 and 340 turns of each of cross-section area 3.2 times 10 to the power of minus 4 meters squared. Calculate the maximum magnetic flux through one turn, just one turn of the coil. So flux magnetic flux, I can call it phi, is of course going to be BA. So because it's just one turn, so it is just BA, where B is, what is B? The maximum B is this one, I think, which is, I think this is 7.2, because the scale is 4 divided by 10, 0.4. So this is 6.4.8, 7.2. So the maximum value of B is 7.2. So it is 7.2 times 10 to the power of minus 3. Then times the area, which is 3.2 times 10 to the power of minus 4. Okay, so I'll press my calculator. 7.2 exponent minus 3, 3.2 exponent minus 4. So this is 2.3 times 10 to the power of minus 6. Determine the maximum rate of change. Rate, this is rate, not the maximum rate of change of magnetic flux linkage in the coil. In the coil, just in that coil, maximum rate. So let's first, we have to look for the maximum gradient from the graph, because the maximum rate of change must be the gradient, because the whole coil must be the gradient times the number of coils times of course times the area, because the gradient is just going to give us the rate of change in B. So let's first find the maximum gradient. The maximum gradient, of course the gradient is delta B divided by change in time. Okay, let's see, where should I expect the maximum gradient? So I'm going to just, let me choose just a very convenient point, for instance, where the graph crosses I think this is a convenient point for the tangent to the graph. Let me try to make this thick, even though you're not supposed to make it thick, just for learning purposes. I want to draw a beautiful tangent. Okay. So here I may not be very accurate for my tangent. I think I should draw a new tangent. Okay, I'm trying to come up with a tangent, so I'll take this point here approximately. Then let me take this point here, almost in the center. The scale is 0. On the x-axis, the scale is 0.1. So this is in the middle of this box. So this is, I want this distance here. So 2.9, that is 1. 2.9 minus 2, that is 0.91. So this is 1.05, I think. Then on the vertical, I'm taking the vertical as this distance here, the whole of this for the vertical, because I'm finding the gradient of this line. So the vertical, I'm taking 8 milliteslas. So my gradient is going to be, let me reduce this, 8.0 minus 0 divided by 1.05, or divide by 2.9 minus 1.85. Or it is 8.0 divided by 1.05, which is 8 divided by 1.05. That is approximately 7.6. Approximately 7.6. You may get a value which is not exactly 7.6. You could be getting a 7.5 depending on how you approximate this, but it's approximately there. 8 divided by 1.05, 7.6, approximately 7.6. Okay, so then let's find the maximum rate of change. So maximum rate of change of flux linkage in the whole coil. So this would now be equal to the number of turns times cross-sectional area times this gradient here. Remember, the rate of change is going to be the EMF, so this will be number of turns. I think it was 340. The cross-sectional area was 3.2 times 10 to the power, was it -4? I'll multiply this by 7.6. I'm saying you might get 7.5 if you draw this on a paper. This could be 7.6, or you could get 7.5. So just check with your paper. So I'll say 7.6 times 3.2 exponent -4, then times 340. So this is giving me 0.86, 0.826. So this is approximately 0.83. So 0.83. So if you use the examiner will decide on the tolerance, but if you use 7.5, you may get 0.82 Weber per second. So if you depending on how you calculate your gradient, the value here, I don't think it may be exactly 7.6 because you'll be using a ruler on a question paper. You could get 7.5, which would give you approximately 0.82 instead of my 0.83 when you round off. Then state the maximum EMF. Of course, here the maximum EMF, I'll just carry this forward. So this would be 0.83, but I said you could also have 0.82 depending on how you round it off or how you obtain the gradient, because the EMF is the rate of change of flux linkage. Is the proportion the rate of change of the flux linkage. Then so it means the maximum EMF is going to be 0.83. Then on the figure, sketch the variation of the EMF V induced across the coil with T from T equals to 0 to T equals to 6. So remember, when the rate is 0, the rate is going to be 0 at T equals to, let's see which values of T is the rate is where the gradient is 0. At T equals to 0, 1, 2, 3, 4, 5, 6 are the peaks. The gradient is 0, so the rate is 0. So I will say the rate equals to 0 at 0, 1, 2, 3, 4, 5, 6. That means V equals to 0 at those values of T. So at the values of T, where at T equals to 0, 1, 2, 3, 4, 5, 6, because the rate is the gradient and the gradient is 0 at these values of time, it means V is equal to 0. Then the rate in between here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. In between here at T equals to 0.5, 1.5, 2.5, 3.5, 4.5, and 5.5, V is going to be 8.3, or is going to be maximum. V is going to be 8.3, which is going to be V naught, because the rate is maximum. At these values, the gradient is maximum. However, at if we say at 0.5 the gradient is positive, at 1.5 the gradient is negative. This is positive, this is negative, positive, negative, positive, negative. So the graph crosses the x-axis. So if we say here it is positive, it will touch there. The next one will be negative. Positive, negative, positive, negative. It can also be the other way around. So just draw a smooth curve through these points. Okay, so that would be the graph roughly. That would be the graph. Then the variation of V with the T can be described by V equals to S sine BT. So I compare this with V equals to V naught sine omega T. That is the general equation. Determine values of A and B. Give units with your answers. So we know that A equals to V naught, which is going to be 0.83. Was it 8.3? 0.83. So this one is wrong. It's 0.83. Okay, so that will be 0.83 volts. So A is 0.83 volts. Remember I said, depending on your gradient, it could be 0.8 0.82 volts, depending on your gradient. Then omega is equal to B. B is equal to omega. And of course, omega can be got from 2 pi divided by the period, which will be 2 pi divided by t. What is t from the graph? The period is going to be 1 to 3. I think the period is 2 milliseconds. So the period is 2 milliseconds from the graph. So I'll say 2 times 10 to the power of minus 3. 2 pi divided by 2 exponent minus 3. So that is 1000 pi radians. 1000 pi radians per second. Or I can write this as 3,100. So I'll say 3,100. The units are going to be radians per second, or I'll write 1000 pi radians per second. Okay. So this is quantum physics. The figure shows part of the emission spectrum of visible radiation emitted by hydrogen gas in a star in a distant galaxy. The galaxy is moving away. So it means, remember, this is increasing wavelength. So that means this is the same as decreasing. This is increasing frequency, which means decreasing wavelength. So wavelength is smaller on the right-hand side, so it is greater on the left-hand side. Explain how the positions of the lines in the emission spectrum seen by an observer on the Earth differ from the positions shown in the figure 8.1. Remember, the galaxy is moving away. That means the stars are going to be redshifted, so the wavelength is going to be longer, or the frequency is going to be smaller. So I will say movement of the star or the galaxy, movement of, can I say galaxy or stars? Okay, let me just say stars because they're in the galaxy. Movement of the stars causes change in observed wavelength, or you can say frequency. Now somebody will say, do stars move? The stars do not move, but because the galaxies in which they are found is moving, so it is what I'm actually referring to here. The stars are not moving themselves, but because the galaxies are moving, then the stars are moving with the galaxies. It's like when you are in a car. The car is moving, or you could be seated in one place. So we say you are still moving, but in the actual sense, you are seated. So the movement of the stars causes a change in the observed wavelength or frequency. So this causes redshift. So this causes redshift. So this causes a redshift. Hence, the observed wavelength is greater than the emitted wavelength. So the observed wavelength is going to be greater than the emitted wavelength, or in terms of frequency, or the observed frequency is lower than the emitted frequency. So on the figure, draw the three lines in possible positions in the spectrum seen by the observer. So the lines are going to be shifted to longer wavelength or to shorter frequency, to smaller frequencies. So I'll shift them to the left-hand side. However, because the expansion is uniform, these lines are going to be shifted by the same distance to the left-hand side. So we have to be very careful with this. So I'm very careful trying to measure the distance to ensure that it's approximately the same. So the first one will shift to that point. I'm ensuring that this deviation is almost the same because the expansion is uniform. Okay, so those will be the new positions of these lines. Note that the distance is almost the same by just looking at them. So the deviation is going to be the same. The lines are going to be on to the left of each of those. The lines in figure correspond to electron transitions down to the energy level minus 3.40 electron volts. That is the ground state. One of the lines represents emitted radiation of wavelength 488 nanometers. Capture the energy of a photon of this radiation. So we know that energy of a photon is equal to hf, which is the same as hc over wavelength. So I'll just substitute this. So this is going to be 6.63 times 10 to the power of minus 34, then times 3 times 10 to the power of 8. Divide this by 488 times 10 to the power of nano is negative 9. So 6.63, that is Planck's constant, exponent minus 34 times 3 exponent 8, divide by 488 exponent minus 9. So that is 4.08 times 10 to the power of negative 19. So I'll write here three significant figures because I see three significant figures everywhere in the raw data. So I'll write here 4.08 times 10 to the power of minus 19. Yeah, the examiner will decide the tolerance. Determine the energy in electron volts of the energy level from which the electron transition originates to cause the emission of this radiation. Remember, the final is the final is minus 3.40 electron volts. That is the final. So let's first find the photon energy in electron volts. So photon energy is going to be equal to 4.08 times 10 to the power of minus 19 divided by 1.60 times 10 to the power of minus 19. I want this in electron volts, so I'll say 4.08 divided by 1.6. So that is 2.55 electron volts. So the energy level, I want to find the energy level. So remember, it is from it is from a certain energy level to negative. So let me say energy level En minus 2.55 should give me negative 3.4. So this should give me negative 3.40. So the energy level En is going to be negative 3.40 plus 2.55. In other words, when I add 2.55 to negative 3.40, I should reach the energy transition from which I came from. So this is minus 3.4, that is negative 0.85. So you notice that negative 0.85 minus minus negative 3.40, you should be able to get the energy difference of 2.55. Then determine the wavelength in nanometers of this radiation as detected by the observer on the Earth. So that takes us to the Doppler shift equation. The difference in wavelength is equal to V over lambda. So let's find our difference in wavelength is going to be V. So this is over C naught over lambda. V over C times the wavelength, which is the speed. What was the speed? Oh, the speed is 6.2 times 10 to the power of 6. Okay. So that is 6.2 times 10 to the power of 6. Then the speed of light 3 times 10 to the power of 8. Then they have given us the wavelength was 488. So it is 488. The answer is still nanometers, so I will not change this. So what does this give us? 6.2 exponent 6 divided by 3 exponent 8 times 488. So that is approximately 10 point approximately 10 point, let me just take 10.0, 10.1, or let's say 10 nanometers. Let me check the number of significant figures here. Okay, I can take 10.1 nanometers, that is 3 significant figures. Then the observed wavelength now. Of the observed wavelength is going to be 488. Because it is longer, it is going to be 488 plus 10.1, which is going to be approximately 400 and I think this is 98.1, which is approximately 498 nanometers to 3 significant figures. Then a value for Hubble constant is this 2.3 exponent minus 18. Determine the distance of the galaxy from the Earth. So according to Hubble's law, V is equal to H naught times D. So that means D is going to be V over H naught, which is going to be 6.2 times 10 to the power of 6 over H naught, which is 2.3 times 10 to the power of minus 18. So this is going to give us 6.2 exponent 6 divided by 2.3 exponent minus 18. So that is 2.7 times 10 to the power of 24. 2.7 times 10 to the power of 24 meters. Okay, nuclear physics. State what is meant by binding energy of a nucleus. If you have watched my videos about nuclear physics, this should be a very easy topic. So binding energy, of course, this is the energy required to separate the nucleus of a not the nucleus, separate the nucleons. The energy required to separate the nucleons, those are the protons and the neutrons. So the nucleons of a nucleus to infinity, that is binding energy. Infinity may not be a large distance, but at nuclear level, the forces cannot influence, or the nuclei or the nucleons cannot influence each other. The table shows the masses of two subatomic particles, polonium nucleus and the polonium nucleus. So we have the proton and neutron. For polonium nucleus, determine the mass defect, that is difference in mass. So polonium is having how many protons? So it is written, it has 84 protons, and it has 212 minus 84 neutrons. And I think this is going to be 128 neutrons. So the mass defect, therefore, is going to be total mass of the nucleus, which is 211. Don't mind about the direction, or you may get a negative, the magnitude will be the same. So let me start with total mass of the nucleus, which is 211.942749 minus total mass of the nucleons, which will be 84 protons times the proton proton mass, which is 1.007276. Then plus the other one is 128 neutrons times the mass, which is 1.008665. So I'm going to press my calculator. Let me start with the bracket. 84 times 1.007276 plus 128 times 1.008665. So I will subtract this from 211.942749 minus the answer. So I am getting 1.778. I'll just have at least 4 significant figures. So the difference is 1.778 in unified atomic mass units. I said I just found a difference. So whether you get a negative doesn't matter. You could get total mass this side minus mass the other side. So it's just 1.778 U. We want the answer in kilograms. So this is 1.778 times 1 U is 1.66 times 10 to the power of minus 27. So I'll just say 1.778 times 1.66 exponent minus 27. So that is 2.95 times 10 to the power of minus 27. Remember I said you might have got a negative here, but I said you just want a difference in mass. So you can find total mass of the nucleons minus mass of the nucleus, or mass of the nucleus minus total mass of the nucleons. Then the binding energy, of course, energy is equal to the mass defect times c squared. So the binding energy is going to be equal to the mass defect, which is 2.95 times 10 to the power of minus 27, then times 3 times 10 to the power of 8, but this should be squared. So I'll just set that times 3 exponent 8, but this is squared. So I'm getting 2.66 times 10 to the power of negative 10 in joules. Then we want binding energy per nucleon. So we get the binding energy per nucleon will be equal to the binding energy, which is 2.66 times 10 to the power of minus 10 divided by the nucleon number, which is 212. So divide by 212. So it's approximately 1.25 times 10 to the power of minus 12. 1.25 times 10 to the power of minus 12. Okay. The examiner decides the tolerance. So On the figure, sketch the variation with a nucleon number A of the binding energy per nucleon for values of F from 1 to 250. So I'm going to divide this range into approximately equal parts. Let me divide it into parts where it is intervals of 50. So let's say from 1 to, let me see how many parts I can divide here. So I think halfway is this. Halfway is almost that. Let me divide this into 5 parts. Let me say this is approximately 50, 100, 150. No, that would be small. I have to rethink this. So if I say this is approximately 50, 100, 150, 200, 250 approximately. So this is approximately 50. Remember the region of stability is around ion 56. If this is 100, 56 is very close because in the center it is around 75. So 56 is very close to 50. So the peak is going to be around here. The peak is going to be around here. Of course, I'm using a ruler to estimate the position of the highest point should be around here. So I'll just sketch the peak around here. Then on the left hand side it is less steeper. I think that is going to be the graph. The peak is going to be on the left of this figure here. It should be on the left of that figure, and on the left of this figure 9 it should be steeper, and on the right it should be less steeper. So the peak is around here where we have ion 56. Okay, so on your line on the figure, draw an X to show the approximate position of polonium 212. So if that is 100, 150, 200, so polonium is going to be somewhere here on the left hand side of the letter A. I mean on the right hand side of the letter A, so it's going to be around here. Around here. So I'll label this X. Or they said draw an X to show the up. Okay, so let me rectify this. So the X is around here. Okay, so I've finished to sketch this. I've drawn the X. Polonium is radioactive and undergoes alpha decay. Suggest and explain with reference why the alpha decay of polonium results in release of energy. When polonium releases an alpha particle, let's check the formula. Polonium, it is 212. It is giving us an alpha particle plus a new nucleus X, whose nuclear number is now 208. So notice that the nuclear number has shifted to the left-hand side. And when you move from 212 to the left-hand side, it means the binding energy per nucleon is increasing. So it means this is going to result in release of energy. So I will say the nucleus formed as a result of the decay has a lower nuclear number. In other words, we are shifting to the left-hand side, has a lower nuclear. We are shifting towards the peak, has a lower nucleon number. So this reaction results. So this reaction results in increase of the binding energy per nucleon. So they are, because 208 is to the left, it is closer to the peak than 212. So it means its binding energy per nucleon is going to be higher. So this reaction is going to result into release of energy. As simple as that. I think this should be the last question, which is astrophysics and cosmology, maybe. Oh, it's actually medical physics. Describe how reflected ultrasound pulses may be used to obtain diagnostic information about internal structures. Remember, the reflected has two features. One, we look at the intensity, and two, we look at the time delay. The intensity gives us information about the nature of the boundary, and the time delay gives us information about how deep the boundary is from the surface. So I will simply say intensity of a reflected pulse gives information about the nature of the boundary. That is one. Number two, the time delay. That is the time it takes for the pulse to reach, to go and come back. That is the time delay. The time delay gives information about the depth of the boundary. So that is how the reflected ultrasound pulse is used. Then define acoustic impedance. We know that Z is equal to rho times C, where rho is the density of the medium and C is the speed of the ultrasound in that medium. So this is going to be the product of the density of the medium and the speed of ultrasound in the medium. So the product of the density of the medium and the speed of ultrasound in the medium, that is acoustic impedance. The table shows some data for water and for glass. Okay, determine the intensity reflection coefficient. Of course, this is alpha for ultrasound that is incident on the water, on a water glass boundary. So at the boundary, we know that alpha is equal to, say, Z2 minus Z1 over Z2 plus Z1. And this is going to be squared. Let's say for the water is Z1, and for glass, let's say it is Z2. Remember also that Z is equal to rho times C. So just substitute. So this is going to be Z2, which is 2500 times 4560. That is Z2 minus 1000 times the speed, which is 1420, divide by 2500 times 4560 plus 1000 times 1420. Remember, this should be squared. So let me try to simplify this. So you have 2500 times 4560, then minus 1000 times 1420. So that is 998 and 4 zeros. 998 and 4 zeros. 1, 2, 3, 4. Divide by 2500 times 4560 plus 1000 times 1420. So this is 11542. How many zeros? 2 zeros. I mean 4 zeros. 1, 2, 3, 4. Remember, this is squared. So I'll just cross out these 4 zeros and I'll simply say 998 divided by 11542. So this is 0.0. Let me check this again. So 2500 times 4560 minus open brackets 1000 times 1420. 998 and 4 zeros. 2500 times 4560. Okay. Then plus 1000 times 1420. So I'm getting something different. 1282 and 4 zeros. I think I made a mistake here. So this is 1282 and 4 zeros. Okay, so I cross out those 4 zeros. Let me divide again. 998 divided by 1282. But remember, this is squared. So this is giving me 0.61. So this is 0.61. Of course, this is a ratio, so it has no units. So the answer is 0.61. I don't know that there's another question. I see blank pages, so that is the end. Yeah, I think I've tried my level best. If I may not be 100% correct, but at least I've given my best. I have around 6 spare minutes. Until next time, bye-bye.
Thank you for supporting my channel. You have made me very popular and am grateful. Thanks to the students all over the world, especially Pakistan, India, Bangladesh, Rwanda, Zambia to mention but a few. You have been the greatest fans in my teaching career. Thank you for always watching my videos, giving suggestions on, asking questions, making constructive criticism and corrections. I love you so much and wish you success in your academics. Continue sharing the channel with anyone involved with Cambridge Physics. If you are new to my channel, please consider to subscribe and share and like the videos. Hit that like button and bell icon to keep updated. Thank you so much.